Okay, let me also record this. Okay. And share. Okay, can you see my screen?
Yes, the screen is seen.
Yes. Okay. Yes. So since this lecture is a little bit maybe long, so I start that immediately without any review on the previous lecture to have enough time to reach to the end of this, hopefully. But if you have any question on the counter, please ask at the beginning. Okay. Okay, so if there's not any question right now, let's start lecture 7 regarding sensor scaling using math functions. In fact, in this lecture, first we study what is analog signals and what's the meaning of what do we mean by sensor scaling, and then we know that and we see that to implement that scaling, we need math functions. So we study math functions and then use those math functions to implement scaling of the sensor data. Okay, I'm sure you are familiar with these concepts, but let's review them together. A digital signal is a signal that has two states in control system or in PLC. When we say it is a digital signal, we mean that it has two states, on, off, close, open, or something like that. In PLC, a digital signal represents by a single bit. By a single bit, this single bit can have two states, 1 or 0, 1 and 0. And so on and off could be 1 and 0, or close, open, 1 and 0. The value 1 and 0 can represent on, off, open, close, or something like that, high, not high, or something like that. This is digital signal. But analog signal is a signal that changes in a range. It's the value of that is not just two numbers. It changes in a range. For example, the level of a tank, the temperature of a room, or something like that, changes in a range. And we want to know how much is that, not just whether the temperature is high or not high. We want to know exact temperature of the exact temperature of the room, or the exact level. These are called analog signals, even when we represent them by binary data in the PLC. We still call them analog. We still call them analog in the PLC. So, for example, if you have a level transmitter to measure the level of a tank, okay, and we want to indicate that, well, on some indicator to the operator, first we should read that. To read the analog signal, we need an analog input module that we will look at some detail on that. Then we have the data, and then we can do some processing on that, anything that are required. And then again, if we want to indicate that in an indicator, show that in an indicator, we need to send that using an analog output module to send that or transmit that to the indicator. Analog inputs, some example of analog inputs, all the sensors, let's say, all the sensors, analog sensors, liquid level, gas flow, distance, viscosity, speed of the car, temperature, like this. Lots of analog inputs. For the analog outputs, signals also are the commands that we send to the device, but the command is not just on, off. It's not just start to stop. For example, the voltage over the DC motor to control the speed of the motor. Or, for example, the percentage of opening of a valve. It's not, the valve is not going to be only open or close. The percentage of opening, okay, it's a position, it has a position. So the percentage of opening, 10% open, 12% opening, how much to be the opening of the gate or of the valve. So these types of commands are the commands that we send. We need output, analog output to send them, or even indicators. Of course, indicators is something like this. We want to indicate that in some indicator device. So we need them. So we need analog input and analog output to for our analog signals. Okay. Practically, there are lots of sensors. I don't know how many type of sensors we have, but practically hundreds or thousands of types of sensors and variables, temperature, pressure, different type of different sensors to measure pressure, different sensors to measure temperature. So there are lots of sensors, and it is impractical to expect that the PLC can understand the original signal that generated by those sensors. Every sensor initially generates some signal. Like for example, a thermocouple, it generates a voltage. PT100, the RTD, resistance temperature devices, that the resistance of the temperature changes. Or any other sensors. It is impractical that we expect that a computer system or a PLC can read all of these. Technically or practically, every sensor has a transducer that converts that signal to some standard electric signal, voltage or current signal. So the measurement could be, the actual sensor can be a resistor sensor, an RTD, or a thermistor, that the resistance of the resistor changed by the temperature, and so we can detect the temperature. But that change in the resistance is converted or represented by a voltage in a range, in a standard range. So all of the sensors, when they measure the measurement, they measure the variable, then they generate a kind of electric signal, a standard electric signal, voltage or current. Of course, there were and there are still some pneumatic standard signals, but let's, because we're working on the PLC, so, and the PLC can only accept electric signals, so just let's concentrate on the electric signals. So the actual variable, which is a temperature, which could be a level, could be pressure, could be pH, could be concentration, or any variable, they measure by sensor, any type, the type of sensor that is selected, but the sensor transducer generates a signal, an electric signal, in some standard electric signal that represent that. For example, if the temperature changes between, I don't know, 20 degrees to 900 degrees, for example, centigrade, okay? This is the range of the temperature that is measured, okay? The sensor measure this and then generate a signal in the range of 0 to, for example, 10 volt DC. It means that if the voltage is 0 volt, the temperature is 20. If the voltage is 900, the voltage is 10 volt. So this is the signal that transmitted from the transducer to the PLC. PLC read this voltage, and then it is the duty of the scaling, this is something that we will study, to read this and then translate that, let's say, or scale that to the actual range, to understand that, let's say. The PLC read this, and then according to our program, we can understand that, okay, if the voltage, for example, I don't know, it's 8 volt, it means that the temperature is something around 700, for example, degrees centigrades. So this is something that we should do. This is something that we call scaling, that we will go to the detail on that. But this is the standard voltage, the standard signal. So there are some. It's not just one standard signal. There are some standard signals. These are the main signals. There are a few more. But most of the signals that use is as the standard signals, electric signals using the sensors are these. They could be voltage or could be current. So that, for example, 20 to 900 degrees, for example, centigrade, can be represented by this signal. It means that 1 volt for 20 and 5 volt for 900. Okay, or 0 to 5 volt, minus 5 to 5 volt, again, minus 5 to 5 volt. This can be also in the current signal. So 4 milliamp means 20, and 20 milliamp means 900. There are some benefit, some advantage on using voltage over current or current over voltage. I'm not going to go through the detail on that. We don't have time to go through the detail on that. But generally, as a general concept, voltage signals are very simple to be generated and read by the PLC. But the problem is that there are two disadvantages of them. One of them is that they are more sensitive to the noise. Noise has more effect on the voltage signal than current signals. The second that is more important is that the length of the cable, wires from the sensor to the PLC or to the has effect on the reading, because there could be some voltage drop over the wire, and so there could be some inaccuracy on reading. But for the current signal, no, there's not any effect of the length of the cable on the current signal. If you have, for example, I don't know, 10 milliamp at the sensor, you have exactly 10 milliamp at the PLC. The current is not, that does not change. But for the voltage signal, if you have, I don't know, 3 volt on the sensor, at the output of the sensor transducer, the voltage that reach to the PLC can be 2.95, for example. Okay, very small change on that because of the length of the wire. So generally for small scale systems, an equipment, a machine that the control system is very close to the machine, is sometimes mounted on the frame of the machine. The voltage signal used frequently. Okay, let's see. Are there anything wrong here? No. Okay. Good. Let me just be sure. Can you hear? Can you see the screen? I just want to be sure.
Yes, we can.
Yeah. Yeah. Okay. That's good. I just wonder maybe there was some problem. Okay. But for long distance measurement, for example, in the power plants, in the cement plants, in the refinery, and like that, we prefer to use current-based signals. Okay. This S7-1200 Siemens PLC provides two analog input. So we can measure two analog input by this PLC. Of course, it is possible to add some extra modules, input modules or output modules. I'm not speaking about that, just the base of the PLC, the one that you have in the trainer. It has two analog inputs. It supports two analog inputs, so you can read two analog inputs. It is possible to add something that called add-on device, this device that you see here, which in the PLC that you have in the trainer, it supports also one analog output. So this PLC supports two analog input and can generate one analog output and send that to the output device. So it has two analog input to one analog output. That's sufficient for very small scale operation. Okay. The standard of the analog input are the two analog input that supports by this PLC is voltage based. It's a voltage, so it does not support current based the voltage, and the voltage, the standard range that it can read is between 0 and 10 volts. So out of these table, all of them, it can this is this is the signal that is supported by this 1200 PLC, Siemens PLC, the one that we are going to, that we work with that, based on that. It does not support others. Generally, advanced PLCs support more than one standards, but for these simple PLCs, it is sufficient. Okay. For the voltage signal, it's very simple to be connected to the PLC. Just directly we connect the sensor to them. This is a single-ended, so it means that the ground is common. So the ground of the sensor and the ground of the PLC are the same. So they are connected. They have common ground, let's say. So we should connect the ground of the sensor to the ground of the PLC, and then the analog input directly connected to the analog input signal terminal. Okay. Okay. How the analog input, the PLC analog input, read that voltage? Okay. The sensor read the measurement, read the actual physical value, let's say variable, the temperature, for example, and generate some voltage. And that voltage transmitted to the PLC, and PLC read that. How? In fact, PLC works as a digital voltmeter, or in this PLC voltmeter, of course, if they support current signal, digital ammeter, but digital voltmeter. So it read the voltage and generate a binary signal that represents that. So it read the voltage, for example, 0 to 10 volt, okay? And then, according to this voltage, it generates some binary signal. The binary signal in this PLC is between 0 and 27,648. So it read this voltage and generate this binary signal. This is the binary signal that is available in the program. So when we read this voltage, with this signal, we can understand, of course, we should work on that in the program, but this means that the voltage, for example, if the binary signal is 0, so the voltage is 0. And if the binary signal is 27,648, it means that the voltage is 10 volt. So on the other hand, let's again check our example, 20 to 900 degrees centigrade, okay? So it means that if the binary signal that we have, we read is 27,648, it means that the temperature is 900. If the binary signal is 0, it means that the temperature is 20 degrees centigrade, for example. There are linear relation between them. These represented by the voltage, and this voltage represented by this number. Okay, you are familiar with binary number. I'm not going to go through the detail on that. It's just a string of 0 and 1 that with some weight. That according to that we know how much is that. For so the physical variable, the boiler temperature, for example, sensed by the sensor, and using the transducer, we have an electric signal here. Electric signal 0 to 10 volts. So here is 20, for example, to 900 degrees centigrade, for example, and then we have 0 to 10 volt. The PLC analog input read that and generate a binary in some range with some number of bits. We'll see what's the effect of this number with some binary number. For example, in this figure, it represented by a 12-bit data, binary data. So 12-bit binary data. And for a 12-bit binary data, I think, I'm not, yeah, a 12-bit binary data can represent any value between 0 and 4096. If I don't, 96, if I don't make it. 1024, yeah, it should be this, 4096. This is the number that is generated. This is an example. Please note it, this is not for the PLC that we have 1200. This is just a typical example. Okay, so for example, a 12-bit binary signal. But you know that in computer, the standard format of the memory size is 8 or 16 or 32 or something like that. Okay, so if the number of the bits are less than, for example, in this case 16, what the PLC adds some zeros to that, some just zero, constant value 0, to make them a 16-bit binary signal. And this 16-bit binary signal stored in the memory, Okay, so this is the analog input card or analog input module. This is the transducer, and this is the memory of the PLC. Memory of the CPU, memory in the CPU card. Okay, so this is the structure. The sensor senses the variable, generates some voltage, the analog input card read that and generate some binary. That how many number depend on the resolution of that. We'll speak on that in a few minutes. That binary number generally or in many of the cases for many of the analog input cards are not according to the number of the bits, are not consistent with the number of the bits that any memory cell has in a computer systems or in computing systems. So the PLC add a few zeros to that and then to make it as a standard 16-bit. But this part is not something that we need to take care of that. This is something just to know that. We don't need to care of this. We don't need to, we just read that and know that the signal is, for example, in this range. And we work with this range. We are not, we don't need to take care of this part. This is something that the PLC itself take care of that. Okay, what is the effect of the number of the bits? If, for example, let's assume that we have this blue signal as a voltage between -1 and 1 volt, just a simple example. So let's assume that this signal is between -1 and 1 volt, okay? And the signal, the actual physical level voltage, the actual voltage is this blue signal. And just as an example, assume that the analog input card has just 2 bits. It has a 2-bit binary, generates a 2-bit binary value. For a 2-bit, it's very small, just as an example. A 2-bit binary signal represents, can represent just 4 different, they can distinguish 4 different binary values, 0, 0, 0, 1, 1, 0, 1, 1. And if we are going to represent a signal in this range by these 4, for 2-bit binary signal, it means that by these 4 binary values, it looks like this, like the red signal. The red signal. So, in fact, for any value that is in this range from -1 to -0.5, it is represented by 0, 0. Any value between -0.5 and 0, it is represented by 0, 1. Any value in this range, it is represented by this, and any value in this range represented by this, because there's not any other value, binary value in a 2-bit binary. 2-bit binary is very small, just as an example. There's not any other. So we can represent them, any signal in this range, any part of the signal that is this range, for example, these parts, okay, this part, all of them just by 0, 0. It means that if later we convert this to voltage again, if we want to convert this to voltage again, to a voltage signal, the signal is something like this red signal. And you see that, okay, the red signal somehow follow the blue signal, the actual signal, but it's not accurate. there's a big error on that, or let's say a large difference between the actual signal and the signal that is represented by this red signal. This red signal, let's say, it means that any value between -1 and -0.5 is represented by -75. Any value in this range is represented by -0.225. Any value in this range is represented by 25, and any value in this range is represented by 75. Please notice we have just 4 representation available by the binary, by the 2-bit binary. Okay, to improve that reading, or let's say to reduce this error, this error is called quantization error. Quantization error. To reduce this error, we need to increase the number of the bit. By a 2-bit binary, we have just 4 binary value that can be represented by this. But if you have 3-bit, for example, it increases to 8. If you have 4-bit, it increases to 16. So you have 16 distinguished, and you can increase that to the number that you need. For example, if it is a 16, and this time again -1, for example, to 1. Okay, this time you see that this blue signal can be represented by these red signal. That the difference is much smaller. The difference is much smaller than the previous one. We have 8 different distinguished value level compared with 4 distinguished levels. So the error, the quantization error reduces by a factor of 2 as you increase the number of the bit one by one. So for a 12-bit signal, we have 4,096 distinguished binary number that can be represented by this 12-bit. So the whole range divided to something around 4,000, let's say, 4,000 division, and for each division we have a number. So the error of that is, let's say, it is in the order of 10 volt. The quantization error is 10 volt divided by something around 4,096. Very small error that is sufficient for many of the typical applications. For this PLC, the PLC that we are using, it is this value. So the quantization error is 10 to the 27,648. Very, very small. It is in the order 12764 approximately. So very small value. So it is sufficiently accurate reading of the analog signal. So that's sufficient for nearly most of the applications. Maybe very less than 1% of the applications in the industry, we may need more accuracy. This accuracy is quite even less than 1%, I can say. It's just some special applications. Okay, so this is regarding the number of the bits. In fact, that 0 to 227,648, in fact, represented by 15-bit is a 15-bit binary signal. It's a 15-bit. So there's one more bit that is not used. So the PLC add a 0 at the beginning, and then this is the 16-bit signal that's saved in the memory. So it's a 15-bit. That's a very good, one of the best accurate general purpose, one of the most accurate general purpose analog inputs. 15-bit is very good. Why maybe 12-bit instead of 15-bit? If 15-bit is better, the reason is that increasing the number of the bits increases the complexity of the electronic circuit of the analog signal, analog input, and this increases the cost. So different types are provided. as it is the number of the bits increases, it is more accurate, but it is more expensive. So this is the reason that some brands, instead of increasing the number of the bits for analog input, they use smaller number, like 12 bit is very typical in industry, 12 bit or 13 bit, to reduce the cost, the hardware cost for that. And generally 12, 13 bit is also sufficiently good for a wide range of the applications. Okay. The other thing that we need to go through that is the data type in PLC, and especially we're speaking on the Siemens PLC. Of course, data type in other PLCs are not exactly this, but they also have something like this, something like it, but not exactly. This is regarding the Siemens PLC. Okay, we studied that a digital signal that represented by 1 bit. Okay, this is called Boolean. And this is how we represent them. The structure that we have already used that, for example, input 1.0, output 0.1, or memory 5.4, or something like that. Okay, it is called Boolean signal. And to represent the Boolean signal, we need just 1 bit, a single bit. The next level is byte. A data type that is byte, in fact, is a 8-bit signal, 8-bit binary signal. Okay, if you, for example, in the integer, in the binary structure, it is 0000 to 111181. Okay. In integer, as an integer value, for example, it can represent any value between 0 and 255. 0 and 255 can be represented by a byte. To address a byte variable, this is how we address Boolean variable, and most of the variables that we used was Boolean. We had that in the timer and counter, other types, but I just jumped from that to this lecture to work on that in this lecture. But for the binary, for other types, for the byte, if you want to address a byte, a whole 8-bit signal, this is the structure of that. Input byte, a B after that, and then the memory address, for example, input byte 2, or memory byte 10, okay? It means that in the memory cell number 10, okay, in the memory cell number 10, 1 byte, the memory, because, okay, let me mention that the addresses in the memory of the PLC are based on byte. So when you address the memory of each cell of the memory in the PLC is represented by a byte. So 8-bit, 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 8-bit. So this address, in fact, is the address, for example, this. So it means that this byte number 10. How much is the value of that? It's some value in the range of 0 to 255, or in binary it is like this. We don't use this byte type, but the one that we use is this most of the time is this word. Word, in fact, is 2 byte. It's a 2 byte memory. So it's represented by 16 bits, or let's say it is represented by 2 memory cells. So there are 2 memory cells that use that. For example, and how to represent that by a W. So MW10, for example. Then we say that we address a memory like MW10. It means that it used the memory byte number 10 and 11. So the memory cell number 10 and 11 together are MW11. Sorry, MW10. Okay, so it's very, make it clean a little bit. Oops. Okay, let me draw that again. So, for example, this is important because it is part of confusing and part of the points that we may made a mistake on programming and have some bug in our program. The memory cell in the Siemens PLC addressed by byte, okay, or let's say are based on byte. Okay, so if this is, for example, memory byte number 10, and this is memory byte number 11, okay, if you write MB10, it means this. Okay, that's good. And MB11 is this one. That's good. But when we call that MW10, MW10 is this. This is MW10. So the memory byte 10 and 11 together generates memory word 10. Okay, what's confusing on that? The confusing part is this. What about if I write MW11? MW11 is the memory is a word that starts with byte number 11, and it needs 2 bytes. So 11 and 12 together. So 11 and 12 together, okay? Together creates MW11. And this is confusing. Why? Because we should take care of that. If you have MW10 in your program, you shouldn't have MW11. Because if you have MW11, there's a conflict between them because both of them are using memory byte number 11. One of them as the second byte. This has 2 bytes. This has also 2 bytes. This uses bytes number 10 and 11, and this one uses byte number 11 and 12. And byte number 11 is common. And PLC does not give you any error regarding that there's a mistake on programming. It just uses that, okay? Here, you're addressing a memory byte number 10. It goes and read the memory word number 10. So it goes and read 10 and 11 and use the value for any purpose. And when you address MW11, it goes and read 11 and 12 and do the job. It doesn't give you, it doesn't mention that there's a conflict on addressing. And this is confusing. Because maybe you change the value of this 11, you change the value of MW10, you assign some number to this. When you assign some number to this, not only the byte number 10, but also the byte number 11 changes. And later when you are working with MW11, you don't expect that the value of 11 has changed. But it has changed. It is because of this. So it's important that if you have MW10, the next address, the byte address should be MW12, not MW11 in your program. If you use MW11, there are some conflict, and that conflict is not assumed as an error by the PLC. It just says, okay, this is your program. You select that. And this is confusing, but you should take care of that. Okay, I use 10, I shouldn't use 11, or I should use 11, so I shouldn't use 12. Okay, it is not even based on odd and even numbers. So it means that you can have MW10 and MW12 in your program, or instead you may have MW11 and MW, for example, 13. This is correct and this is correct, that there's no conflict between them. You can start with any cell number. You can start with any byte number. But please take care of that. If you have MW11, it means that you are using byte number 11 and byte number 12. Do not address MW12. Okay? Otherwise, there are conflict on that. The other one is double word. For double word, it is used 32 bits. 32 bits that can represent a very large integer number, for example, integer number. Also, there are others. For the integers, okay, this is regarding the cell of each pack of data. Okay, it could be a boolean, a byte, a word, a double word, 1 bit, 8 bit, 16 bit, or 32 bits. Okay, this is the structure. The value itself can be an integer value, okay, or real value. If it is integer value, There are different types of that. We are not going to use all of them in our programming in this course, but just have a short look to all of them, and then we just use a few of them. Unsigned, U means unsigned, and S means short. Unsigned integer, it's an 8-bit, so a byte address, that there's nothing signed on that. So 0 to 255. This can represent 0 to 255. You may have signed, unsigned short integer or short integer. In short integer, the value can be positive and negative. Out of these 8 bits that uses to represent them, or this byte that represent them, one of the bits are used for the sign. 0 or 1, depending on that, it could be positive or negative. So you have just 7 bit to represent the value of that. So it can represent any value between minus 128 to 127. Okay, and this is how, as an example, just forget this one. This is something that we have not studied. MB byte number 0, for example. M byte number 5, for example. Okay, and it could be signed or it could be signed or unsigned. The typical integer, this is short integer, but the typical integer that we use generally is this one, integer. An integer that represented by a word instead of a byte. So if it is signed integer, it can represent any value between minus 32,768 and 32,767. Any value in this range. If it is unsigned, okay, one of the bits that are reserved for the sign is also added to the number, so it is between 0 and 65,000. This is the type that we generally use in our program in this course. We are not going to use others, but of course you can use them. But how to address an integer value? An integer value needs 2 bytes. It needs 2 bytes, so as a word. MW2. So this is the structure that we use. MW2. So it uses the memory cell number 2 and 3, number 2 and 3 together to represent this 16-bit. 8-bit for each of them. 8-bit for each of them, and so totally we have 16-bit to represent this integer. This is the structure that we use in our program in this course. Of course, as I mentioned, you may use them in others. There are others also double integer that longer 32 bits. So for 32 bits, we need a double type. This double word type for double integer for to have 32 bits, but we use this. For the real also, a real value need 32 bits. So it should be a double word type. It use 4 bytes. We need 4 bytes to represent real. So if you have a real number, please notice if you have the real number and you need to address that as a double word. So MD, for example, 100. And when you have MD 100, it means that the bit memory 100 to bit memory 103, these 4 bits are 4 bytes are used to represent double word 100. A real number is represented by a double word. It needs 4 bits. The range of the values that we have in a word is quite significantly large, between 10 to the power of 38 minus and plus to the power 8, and small, very small value, 10 to the power of minus 38. Very small, very large value, so it is sufficient for most of the applications. In very special applications, maybe we need a long real that represented by 64-bit 8 bytes, but we don't need. So the only structures that we use are these 2, plus, and also we may need either of them, depending on the type, but not this one. This, and this. These 3 from the data types we don't use these in our programming, but Boolean is the one that we have already used. Word or double word, word for the integers and double word for the reals. These are those data types that we use. Okay, so how to, for the analog input, analog output, how to represent them? The format is this: IW and then the byte number, or the let's say the memory number associated with that input. The memory number, for example, IW8, which means the input data is stored in bytes number 8 and 9. 8, so 8 and 9. QW0, output word 0, represent an output that the data is stored in byte number 0 and 1. Okay, the question could be this. Okay, in that 1200, PLC 1200, we have two analog input. What is the memory address for these two analog inputs? What are the memory address? Where they are stored? By default, in this PLC, the analog input number 1 is stored in byte number 64, and of course 64 and 65. So to address the first analog input 1 in this PLC, we should write IW64. IW64, that is memory cell byte number 64 and 65 in the input image memory. Please notice this is in the input image memory part. They have input image memory, they have output image memory, and they have their own address, and they have bit memory. So we have input image memory, memory. We have output image memory, and we have let's say the memory, the memory, the internal memory. Okay, that we use N for that. We use I for the input, Q. When we say that in the byte number 6, it means that byte number 6 in the input image memory section of the memory. So you can, for example, you can have also M64, MW64. There's not any conflict between them, because although the number are, both of them are 64, but this is 64, the byte number 64 in the input image memory section. But this is in the memory section, 64 in that memory section, so there's not any conflict. But for the analog input number 1, input word 64, and for the analog input number 2, it is 66. It is possible, in Siemens PLC, it is possible that you change these memory address, but we don't need to change them. But for example, in the data sheet of this trainer, they changed that to 100, I think. Yeah, they changed this to 100 and 102. But we don't need to change them. But just know that it's very simple to change them. But just let's skip that. This is, but it's possible you may prefer to change the address, the memory address of them. So it is something that you simply can do that in the configuration of the PLC. But let's keep the same memory address as they are. Okay, so let's work on the scale. We have enough, all the basic materials that we need from the hardware and software point of view, and the data types. And now we are going to do the scale. Okay, for scaling, let's review that again. We mean that, let's assume that, for example, in this example, the temperature is between 100 and 500, the actual temperature of the boiler. This temperature is measured by the sensor, and the transducer generates a voltage in the range of 0 to 10 volt. This 0 to 10 volt is read by the analog input card. That analog input card generates a binary value in this range. But the problem is that this is something that is available in the PLC. This is the number that we have, but this is meaningless for the operators. For example, if you say that to the operator that the temperature is 27,000, they just confused. What's 27,000? The maximum temperature is 500 degrees centigrade. What's the scale of that? The reason is that this is just a binary number. One of the duty of the control system or the programming is to scale that to the physical range. So read this binary and do some by applying some by calculation, generates a number that is the actual number, that represents the actual number. Let's call that the scale value. The scale value. We should scale that to the physical range, to the actual physical range. And now we are going to work on this scale. To do a scaling, yeah, this is the question. Let's just skip. To do scaling, scaling is based, generally most of the times scaling is just a linear. We need just to, the relation is linear. So, for example, if the voltage is between 0 and 10 volt, okay, 10 volt, it means that the temperature is 100 to 500 degrees. 0 volt represented by 0 and 10 volt is represented by 27,648. So the relation between the physical variable, the scale value, we call that scale value or the physical value, and the binary or the voltage to the input value. The input value is voltage from the electric signal point of view and is binary from the data point of view. The relation between them is linear. You can represent that by a linear function. And the question is that what is this linear function? And we need to implement this linear function. If you have this linear function, then when we have some binary value, say, for example, I don't know, 14,000, for example, then using this function, we can convert that to the actual physical, for example, I don't know, 300, for example. Okay, the value, the actual value, the scale value. This is we call that scale. Okay. We are not going to extract this formula. The formula, in fact, is this one. How to extract that? I'm sure you know that, or you can simply extract that, but this is the formula. The relation between the scale value and the input value, between the scale value and the input value. The input value multiplied by the slope of this line plus the offset. The offset is this. If you have this is the offset. Okay, this is the offset. And this is the slope of that. So the slope and the offset. Okay, so if you have the slope and the offset of this line, and then if you have some input value, we can simply use this formula to find out the scale value. But how to calculate the slope and offset? For the slope and offset, if the range of the physical value is between some scale mean and scale max. Okay, so for example, 100 and 500. This scale mean and scale max values are represented by some minimum input and maximum input mean and input max, maximum value of the input. Okay, so this minimum input or input mean and input max, they represent scale mean and scale max. If we have these values, we need these four base values to know what is their range. Okay, this is now by the PLC, we know by the PLC card, looking at the manual of that, we can read that. Okay, for example, for this PLC, Siemens PLC, it is in the range of 0 to 27,000 something. And what is the scale, the range of this? This depends on the transducer and the sensor. And the sensor let us know. Okay, if the sensor output is between 0 and 10 volt, how much is the temperature? The temperature in this example is between 100 and 500 degrees centigrade. So we know these two values from the sensor or from the process and the sensor, and these values from the PLC. Okay, then the slope formula is this: slope scale max minus scale mean divided by input max minus input mean. So it is 500 minus 100 scale max by scale mean divided by input max 27,648 and input mean. That gives you something like this value. For the offset also it is this: scale mean 100 minus input mean is 0 because it's between 0 and 27,000, multiplied by slope, and slope comes from this. So it is simply 100. So this formula for this example, this is the general formula. For this example, the formula that we should implement in the PLC is this: scale value equal to input value multiplied by this number plus this. And so if you have this input value, for example, input value 64, by using this input value and multiply that by this number and add 100 to that, we can find out how much is the scale value, how much is the temperature in degrees centigrade. Okay, we are going to implement these functions. The raw data that we have are these: scale max, scale mean, input max, input mean. So we are going to calculate the slope, prepare the program to calculate the slope. A program continue that to calculate offset, and then use these two to implement this scale value formula. Okay. The math functions are in the instruction tab. We have comparator. These are the functions that we need typically for doing math. Comparator operators, math functions, move operators, and conversion operators. Of course, in this session, we only use these math functions and move. For the comparator and conversion, we use them in the next lecture. In the next lecture, we have the program that we use this comparator and conversion. So just we use only the math function and move. Okay. Each of them, if you open each of them, there are lots of functions. We are not going to go through all those detailed, all of those instructions, just a few of them that to start and those that we need for this scale. Okay. The first function that we need is move. Move function or move instruction is used to assign a number or some value to a memory. For example, here, I want to have a memory that represents a scale max. And that value is going to be 500. That memory is MW22. Okay, this is the memory that I store the value of a scale max. And then later I use this memory for the calculation. But the value of that is going to be 500. I can use move to assign 500 to this number, to this memory. So the input of this move function can be just simply a number, depend on the type of the variable, an integer or real number. In this example, an integer number, or this can be another memory address. Maybe I want to copy MW, I don't know, 12, for example, to MW22. I want to copy this memory, the value of this memory, in another memory cell, in another memory word. We can use move. But in this example, we use this move just to assign some number. There are some issues on that. One of them is that you can add a condition for this instruction. For all of the math functions, I think all of them, maybe there are some exceptions, I don't remember, but up to my memory, all of the math functions, you can have an input condition for them. This function operates if this function, this instruction operates if the condition is satisfied. So if here you have logic 1, please notice this is logic 1. So if this condition is satisfied, so this is 1, and so this is 1. In that case, you have 1 on the enable of the move. So there's an enable input for the move. If this condition is 1, then 500 saves on the output. If this condition is 0, this does not save. So you can control that, whether you want to transfer this value to the memory or not. Maybe for some reason you don't want to, at some cases you don't want to memory. Or maybe you want to select, depending on the condition, either this value or another value. So you may have another move that has opposite condition, M3.1. Okay, and in that case, for example, you want to say 1000s in that MW22, for example. Okay, so if M31 is 1, 500 is assigned to MW22. If it is 1, then if it is 1, 500. If M31 is 0, then this is 1. And in that case, it is 1000s that is assigned to the memory. So you can connect. You can also have more than one output. So you can you want to assign this number to multiple variable for any reason. For any reason you want to multiple. Just to add more outputs, there's an icon here. When you in any math functions, if you see this symbol, this icon, it is called create. If you click on that, it adds one more output to that. So every time that you click on this, it adds more variables here. Okay. This is regarding move. There are some other move functions and move instructions that we are not going to go through the detail on them. Regarding math functions, there are lots of math functions. 4 of them are the basic math functions: addition, subtraction, multiplication, and division. These are the basic that nearly all of the PLCs support these. There are some more math functions that most of the PLCs support, but maybe not all of them, like the square root, for example. Square or square root, these two. Square root. Or absolute value. Most of the PLC support these math functions. There are some math functions that supports by advanced PLCs. Siemens is one of the advanced PLCs, so it supports many of the math functions, many of advanced math functions, but please notice it depends on the CPU. So for some of the CPUs of the PLC, the number they cannot support all of the math functions. For many, generally advanced math functions, they support just simple math functions, but most of the typical math functions are supported by all of the CPU types in the Siemens PLC. So, for example, this is for 1200. There are more functions here. So they support this 1200 PLC. Siemens PLC supports many of the math functions. We are not going to use all of them. We need just these 4 basic arithmetic functions. Okay, so you have addition, multiplication, subtraction, division. For each of them, there are 2 inputs. Okay, for example, adding input 1 to input 2, and then save that in output. The same, multiplication, subtraction, and division. All of them has enable input, similar to the move. So if this enable input is 1, then this add functions, runs. Otherwise, it does not run, so the addition does not add it. Okay, for each of these, for the type of the output is important, along, of course, input. The type of the output, whether the output is going to be an integer, a real, a long real, I don't know, a signed integer, unsigned integer, any of them. This is something that you can select by clicking on these 3 question marks. By default, it assumes that automatically. So for example, if this input and this input, both of them are integer, automatically PLC assumes the output to be integer. Automatically. If either of them are real, automatically it assume that the output is going to be real, because one of them is real. And so it assumes that. But you can select. For any reason, you may want to change that. So it's possible to select that. We'll look at that in the program. But these are for the addition and multiplication, you can have more than 2 inputs. You can click on this and have 3 numbers to be added, 4 numbers to be added, or 3 or 4 or more numbers to be multiplied. But for the subtraction and division, there are just 2, because it's confusing. Which one is going to be subtracted from which one? So for subtraction and division, there's not, we have just 2 inputs. There's not more, but for the addition and multiplication, it's possible to add more. Okay, as I mentioned, you can select the type of the output. You can select by clicking just simply on that question symbols here. Then you can select to be the output to be which type, a real type, integer type, and like that. Sometimes if there's a conflict between the types, it may give you an error, and then we should select properly this one. But many of the times we don't need to select it, just the auto is sufficient for us, but we can select. Okay, there's one more output also, ENO. In fact, this shows that if there are any error, or not. If the value of this output is 1, it means that there's not any error. But if it is 0, there is some error. What is the error? Depend on the type. For example, just as an example, divide by 0, division by 0. Okay, if you have division by 0, divide by 0, the ENO output becomes 0. Or divide if both inputs are infinite. If both inputs are infinite, this is also an error. So there are some error. We are not going to go through all the detail, but you can look at that, some of these errors regarding, for example, if one of the variables are infinite, or as I mentioned, this one. So there are some cases that there are, maybe you mean that. Maybe you mean that you want to divide by 0, or for any reason. You want to divide infinite by infinite for every reason. I'm not going to go through the detail why. It depends on the special program. The problem is that the issue is that PLC informed you that this happens, and then you can decide in your program whether to, I don't know, send a message, an error message, or do something, or what to do. It depends on your programming. It just let you know that you divide by 0. And so according to that error, you should take care of that and try to fix that. Okay, as I mentioned, there are more functions like square root, square of that, or exponential. So if in exponential functions, you have 2 inputs, input 1 to the power of input 2. So there are many sinusoidal, trigonometric, all of them are supported by that. Okay, as I mentioned, we are not going to go through all the math functions. We just need those basic arithmetic functions and the move function. These are the only functions that we need. Then let's work on our scaling problem.
Are you there? Yeah. We seem to have lost you. We can't hear you anymore.
We cannot hear you.
Maybe network.
Unakuanga na shida ya network Canada.
Yeah, that is something that is there. Why can't that one happen there?
Hakuna bwana, hiyo ni mambo ya Kenya bwana.
We, Namasaka.
Sema.
Unajua nimeshtuka, nimedhani ni quiz ingine inafaa tufanye.
Siku hizi iko baadaye.
Nimedhani ni sahi. Poa.
Nikaa huko acha si mtu amtext hapo kama message. Alata ametoka, hayuko in.
Ameenda.
Ninaona he has left.
Napiga kelele.
Judy.
Sema.
Mambo.
Poa.
Bale. Nyamaza sana.
Nakwambia assignment zinaniua. Maquiz.
Ati zinakuua ama
Zinaniua. Unajua jana sikujua kuna quiz.
you were not aware that one was posted on the wall.
Sasa wall gani mimi niliona? Wall gani mimi niliona zile?
Okay, but
Sikujua.
What's happening here?
Ama ni stima zimepotea kwao.
Wang'ang'a.
Stima zimepotea na hawana generator.
I can see you now. I can see your face.
Vincent,
Yes.
nasema nini?
I'm saying that I can see you. I can see you now.
Yeah. The teacher is back.
Okay, can you hear me?
Yeah. You can get you. You can get you.
Okay, sorry, there was some, I don't know what happens, but there was just a power outage, just for a few seconds. I don't know, outside is raining, so maybe there was, because of that, I should check that, but yeah, I was disconnected. Okay. Okay, so can you see the screen? Can you see the screen?
Yes, where we were.
Yes.
Good. So, yeah, I don't know what this happened, but there was some power outage just for a few seconds, and then for the internet to restart, it takes times for the internet switch to restart. Okay, so let me continue. So we're going to use those math functions to implement this function. In fact, for the scaling, we need math functions, okay? Siemens exceptionally, of course, maybe some other PLC brands also for, there are three ways, there are three methods, let's say, methods to do the scaling. One of them is through math functions. The other is through a special instruction called calculation. We studied these two in this session, okay? But Siemens also has some special advanced function for scaling, okay? That is just for scaling, an advanced function. I mentioned that the math functions, some of them are basic, some of them are advanced functions. Siemens has a special function for scaling. We will study that next week, next week in the next session, but we're going to use the math functions also as a practice to get familiar with the math functions. So these math functions, we're going to use to implement this formula by the math functions as a practice of math functions. Okay, this is the formula. So we need to first assign some values to scale max and scale mean, also input max and input mean as the raw data, and then calculate these, subtract these, divide them. Then we have the slope. Using the slope, multiply that by the input value, input mean, and subtract and scale. Okay, and then implement this. In fact, when you use math functions, we implement part by part a formula. So first this parenthesis, okay, then this parenthesis, and then divide them. Again, this parenthesis, and then subtract that from this one. This is how we implement them, use the math functions to implement the formula. So let's start. At the beginning, we need to assign the number. So assign 500 to this memory that I call that scale max. 100 to this memory that we can call that scale min. This to input max, this to input min. Okay, this is just assignment using the move, and there's no condition for them. You may have some condition, but we don't need to have any condition in this example. Then here you see that, okay, to implement this, first we need to subtract scale max from scale min. Okay, scale max, subtract from scale min to have the slope numerator, this formula, the numerator of this formula. Similarly, the input max minus subtract from input min to have this slope, denominator. Then divide that. Sorry, it's not correct. Denominator, not the numerator. That's a error here. Okay, so slope numerator divided by slope denominator. Okay, to have the slope division. Okay. For all of them here, these are integer in fact, because these are integer values. So you see that MW0, MW16, MW20, okay? But for the result of all of them, I use MD to have real output. For these, because both of them are integer, it was possible. Both of them are integer, the result could be integer. So I could use MW4, but just to, but somewhere, for example, for the division of two integer could be real. So this should be real. Just to reduce confusion for myself, I assume all of them to be real. All of them to be real. All of the results to be real. Although this could be integer, this also could be integer. But I just assume that all of them are going to be real. So yes, these two are integer, but they divide and the result is a real number. And then you see that, so a real number is selected for all of them. If I selected auto, in that case, this could be MW. It depends also on this, MD4 or MW4. If it is MW4 for automatically, the function, assume this to be integer. But I select that to be real, and if it is real, so it should be a double word, because real need 4 bytes. So it should be double word. And then I have MD4, please notice, it means that memory number 4, 5, 6, 7, all of them are used by this memory, by this MD4. I shouldn't anywhere else have MD6. MD6 is meaningless because it is part of a real number. It is part of the beats that are used by this real number. So this is something we should take care of. That there's not, PLC does not give an error on this. It just uses that MD6. Okay, use that, but it is from a mathematical point of view, it is not correct. Okay, so then multiplication of input and the slope to have the offset term number 2, this term, and then subtraction of this term from this. So subtraction and this the offset. And finally, okay, this formula, input value, IW64, okay, input value, multiply by the slope, so this term, this is this term, and then add offset to that to have the scale value. So if you have this input value in your PLC, then it gives you the scale value as the output of this part of the program. Okay, this is one way to implement this math function. There's another way, there's another method to implement, or let's say there's another instruction in the PLC. There's another instruction in the Siemens PLC. This is special for Siemens PLC. That you can implement more a complex formula. I don't want to say very complex, but anyway, more complex, not that simple. You see that to implement that, we should, when we use this basic instruction, we should implement part by part. First addition, so each time we can implement just one function, for example, the multiplication. Then for the summation, we need another instruction, okay? Siemens PLC provide a special instruction called calculate. By calculate, you can implement the whole formula once, all at the same time. This is special for Siemens PLC. The calculate also is available in the instruction. Let me go back to show you where's that. We'll open this is here. This is the calculate. This is the calculate. Okay, so under the math function, the first instruction is calculate. We use these four for that example, but this time I'm going to do the scaling this time by calculate. This calculate is a special function. It's a special function that you can use that to implement more complex formula all at the same time, all together, not part by part. Okay, this is the general structure of that. It has some input. You can add more input to that. And it has an output and a formula that this formula you can give that. How? If you double click on this, then window pop-ups. Here you can write the formula directly. Let me increase the size. You can write the formula. For example, input 1 multiply by the summation of input 2 plus input 3. Summation of input 2 and 3. So you can, if you're going to use those basic math functions, you need one function, one instruction for this addition, one for this multiplication. But by calculation, you can implement all together. Of course, this calculation function does not support all math functions available in the PLC. It supports some of the instructions, not all of the instructions. The list of the instructions that can be supported depends on the type of the variable, and are written here. So you can use, for example, if the value is real, if your value is real, then you can have addition, subtraction, multiplication, division, absolute value, exponential, I don't know, there are many, fractions, sinusoidal, trigonometric, and many, square root, and many others. So many of the basic math functions can be used here. So you can have a long formula implemented just in one instruction. This is good. It makes it very simple. Readability is good, but we should take care of that, how to use that. And it depends on the type of the variable, and some of the basic functions are implemented. So let's implement this time that scale function, this time with this calculate. Okay. To do that, okay, again, it depends on you should select the type of the variable, and the type of the variable, if you, for example, it is real, so it should be double. This is just something that we have already discussed that. So if the type of the variable is going to be real, please notice it should be the double word. It should be a double word, otherwise there would be an error. Okay, this is something that we have already studied. Okay, so let's this time implement that scaling formula by calculate. Again, we need this assignment. This is something anyway we need that to assign these these values to the memories for the scale max min and input max min. And then for this formula for the slope, we don't need to calculate this and this separately and then divide them. We can directly write them in the calculate. So we have okay. Add more inputs. Input 1 is a scale max. Connect scale max or assign a scale max to the input 1, scale min to the input 2, scale input max to input 3, input min to input 4. And then inside, we just use input 1, 2, 3, 4. And then the formula is it, input 1 minus input 2, so it's scaled max minus scaled min, divided by input 3 minus input 4. So just one single instruction. And it is more readable. This is also interesting. It's not just because the benefit or advantage of using this calculator is not that just that you have smaller number, a lower number of the instructions. It is more readable because you can look at that and say, oh, okay, input min minus input 2 divided by, so you see that the formula is here. So it's very readable. Later, if you want to check something, to analyze the program, it's more readable. But as I mentioned, it is limited. Depending on the type of the variable, some of the basic instruction can be used here. So this is for the slope. Okay. This is for the slope. Then offset, similarly for the offset, just one formula. And finally, for the scale value, it is this. Of course, it was possible to combine all these formula and have some single formula, a more complex single formula, but I didn't use. So you could only have, it's possible that you have just one calculate, just one single instruction, and have all the input variable, the input plus those scale max min, input max min, all of these 5 given to that formula, and have a complex formula to implement, to be implemented and give you the scale value. But just to make it readable, I separately calculate the slope, calculate the offset, and then calculate the scale value. So just by 3 calculate functions. Okay, so this is the one that I can use. And for the HMI, we are going to look at the program and work, run that. For the HMI, here we are going to see 2 more functions in the HMI. One of them is the bar. This bar indicator, so that you are familiar. So the color change, so when the value increases, this blue color rectangle increases. So you can read that. Also, you can have a trend, you can have figure, the curve of changing the variable. Okay, so you can have the trend of change in the variable, these 2. The detail on how to call them and how to assign value to them are given in the recorded session. So please watch that recorded. I'm not going to go through the detail on that, but we're going to use them and see the effect of them. Okay. So this is the program. You have that sensor scaling version 14. In this program, both methods, that is the method for individually using the basic instructions, and are implemented, and also the calculation. So you have 2 output. One output scale value based on individual basic math functions, and you have another output I call that scaled value calculate. Scaled value calculate, calculate. That is the same value, but this time using the calculate function. As I mentioned, there's one more method, special method that Siemens support, that is called directly scale function. This is something that we study tomorrow, next week, on the next lecture. So, but it is also provided in this program. But we're going to only use these two types. So the first part, calculate the scale value based on individual basic math functions. And where are the basic math functions? Okay, let me open that. Okay, here it is under the instruction. Okay, you see that it is testing, but instruction. If you select the instruction, then here you can see the comparator, the math function, move, compare. So if you click on the move, there are many type of move functions. We only use this first one, this move. There are some others for special functions and also math function. The first one is calculate, then addition, subtraction, multiplication, division. And you see that the list is quite long. There are many others. There are many other basic math functions. In addition to these basic math functions, okay, there are some more functions like the conversion, as I mentioned, the conversion that directly calculates do the scaling or like that. But let's work on these. For the HMI, again, let's see the HMI also and then simulate that. In the HMI, again, we have two screens. The root screen, that in this root screen, we have just the, okay, 3 bars. This bar shows the analog input in that binary value. The binary value, or let's say the decimal representation of that binary value. So it is unscaled value. So the raw data that read by the analog input signal, and here is the scale value calculated by the math functions, and this is again the same scale temperature by the calculator. For this one, for the scale temperature by math, if you click on trend, then a new screen opens. We will look at that, we simulate that, but a new screen opens, and inside the screen, this new screen, you have the figure, and here the plot of that during the time change of the values during the time shows on that. Okay, let's simulate them. So first, let's compile. There's not any error. Okay, and regarding the HMI, again, let's compile this HMI also. No error. Okay, so one by one, simulate first the PLC. Instead of downloading, just click on simulate. Okay, PLC stream opens, and then, okay, load, and a start. It doesn't start. Was there any error? No. So, I think I had another. Okay, I had another PLC. Okay, let me just close this one. I noticed that I had that another one. Oh yeah, I had this one also. This is the one that starts. Yeah, this one. Because okay, let me just stop and close this one. Okay, and once more do that, because I had already opened that simulate before. There was a conflict on that. So let me just again click on this. Yeah, this opens, that's correct. And then that was also correct, but there was 2 simulator opens, so it was confusing. Okay, so this is the PLC, and regarding the HMI, also let's select the HMI and then simulate the HMI. Okay. Okay, this is the HMI. And if you click on this trend, okay, the trend opens. The trend shows the value during the time. Okay, we'll look at that again. So let's go back and let me just a little bit here. This goes here, save some space. Okay, I want to make it minimize. Oh, not that much. Okay, in the PLC, the program, this is the program block. Okay, open that. Yeah, click on this to monitor the values inside the PLC. Okay, here is the PLC. Let's look at some of the parts of that when it is running. So 500 is assigned to MW0. So you see that the value of that is 500, or 100 is assigned to MW16. 100 is the value of that. Okay, let's go down. And then, for example, 500 minus 100, it is 400. And since it's going to be real, you see that there's a floating point here. You see that decimal point here, 400.0. This indicates that this value is a real value. But here, there's not any decimal point. So it means that this is an integer value. Okay. And then for the input, as I mentioned, the input value, in fact, the input of the PLC is IW64. IW64, but this is simulator. We don't have any input, physical input. So I replace that by MW64 in this program. Of course, in the program that you have in the site, it is IW64 because it's based on using the trainer. If you're going to use that as a simulator, just change this to IW64. To do that, let me show you again. Here in the PLC tag, it's better. You can change that here, but if you use this variable anywhere else, you should go all those points and change that. A better way is to open this PLC tag, okay, show all tags, and then simply here, analog input, okay, just change that from here. It was IW64, or it is IW64 in the program that is available to you. I changed that to MW64 for the simulation purpose. So here it is MW64. Okay, so let me minimize that. And then I'm going to change this and see, let's see the effect of that here on this figure. Okay, let's see the change here. Okay, for example, let's assume that this value could be any value between 0 and 27,648. So let me change that. Oh, what's that? Okay. No, sorry. What happened? Oh, yeah, this. Oh, yeah. Double click on this, and then this opens. And here you can modify the value. Let's, for example, 10,000s. Let's see what will happen. Okay, you see, 10,000s. This 10,000s is equivalent to something around 245 or something like that. For both cases, you see that both are the same because they implement the same value. So for example, let's change that to 27,000, for example. And here you see it is very close to 500, and here you can see that it is very this. Click on the trend, and then here you can see the change on the value during the time. Initially it was 0, which was equivalent to 100. And the red signal is the analog input, and the blue signal is a scale value. So initially it was 0, and the scale value was 100. Then I changed that to 10,000s, and this also changed to something around 245, and then 27,000s with this value. So this is, as I mentioned, and these are scales. The vertical scale. The left side is for the temperature and the right side is for the analog. So for the analog input, the actual input. So you can have two different scale for different variables. So you can have different multiple. You can plot multiple variables that change the trend on multiple variables in the same figure. And this is one of the important, let's say, tools that we need in the HMI. Okay, as I mentioned, the detail on how to implement this function and how to implement the PLC and the HMI is given in the recorded, so I don't go through the detail on that, just to see how it works. It was a very fast and complex session, but I should go through all of that together in one session. So yeah, it was very fast. Okay, if you have any question. Any question? Any comment? Okay. So let's stop at this point. Next week on Tuesday, we'll have the last session. We'll have the last session, and also you will have the quiz. The quiz at the end of that, okay? At the end of that, something around 10:30. Yes, on 10:30. Of course, since the next session is the last synchronous session, so we should finalize everything. So if there might be some change on the time, but the time is 10:30 for the, sorry, for you, 5:30. 5:30 is the quiz time. But if for any reason the course like this, like today, need more time for the lecture, we may postpone, shift that the time. But the quiz starts at 10:30 or at the end of the next sessions. Next session is the last synchronous. I want to again ask, could you download the program and install that PLC sim and the program and start working with them? Please let me know if you have any difficulty on downloading, on installing, and starting working with the PLC sim. It's very important that you start working with them to get familiar and then do your assignment. Okay, any question?
No question. I just tried to download it today, and the only challenge was the Wi-Fi was slow, but I managed to reach that part where you can download. I had downloaded the first part, so I hope by tomorrow evening I'll have all the 5.
Oh yeah. Yes, it's a very large, something around 7 gig. Yeah, it's a very large. Yeah. PLC Siemens PLC is very complex and very advanced. But yeah, this is a problem. It's very complex. It is a large program, and also it has lots of options, lots of functions that it takes time to get familiar with that. So yeah, I know it's a very large program. I also do the same. I download that part by part and then finally combine them using that Excel. Okay, yeah, I know this happened. So please do that, and then start work, install and start working with that. If you have any question, we can have extra meeting to work on that if you need any question. But I try to explain the detail on how to use that step by step in these recorded sessions. In the recorded sessions, all the details are given, or at least I try to give you all the detail. Instruction, the detail on how to use that. We are not going to use all the functions. It's very complex program, and it's better not for the first, let's say, try, not to try to use all of them, because it's very complex and sometimes confusing. So just part of that are needed for a basic start and initial start. Then you can when you get familiar with those initial parts, initial functions, then you have enough time to work with others and get familiar with others. And me also, and most of those that work with the PLC, many times there are some instructions that we notice, oh, what's that? We never see that. Oh, okay, in that case, we should go to the manual and read the user manual and then find out what's that instruction. So it is very typical that it's very difficult to, let's say, memorize or many of the functions are just for special cases, for very special cases, for very special applications that maybe more than 99% of the practitioner never use them, but they are there. It is there. If you need that, okay, it's there. So yeah, but try to download and start working with that. It's a very interesting PLC and very interesting software. Any other question?
Okay,
I also said, oh, sorry.
Yeah.
Can I proceed?
Yeah, go proceed.
I managed to download the software, and when I'm installing it in my machine, I don't know where the program goes, because when I go to my program files, I can't see them. So I don't know whether it is issue with my computer or there's a problem.
Okay, there are 5 files. 4 of them are large, 3 of them are 2 gig, and 1 of them is in the order of 1 gig. And there's one very small size file. It is an exe file. All of them should be in the same directory. So download them, all of them in the same directory, not in different directory. When you save all of them in the same directory, then run that exe file. When you run that exe file, the 5th file in the Siemens site, there was 5 files. The last one is an exe file. It's just a few kilobytes. When you run that, it automatically reads the data from all 4 others and combine them, mix them, and then start to install them. Could you see all those 5 files in the same directory? And did you run that exe file?
Yeah, I have them in the same location.
Okay.
And I ran the Excel.
And what did happen when you run that exe file?
When I ran it, it asked me some questions about installation, which were just basic questions.
Yeah.
And I went through that up to the last one was finished. So when I finish,
okay,
it suddenly disappears.
Okay, disappears. And did you check that you have that TIA, something like this, TIA search, or you may open this and then under the Siemens?
No, this
automation. Did you have these?
No, I couldn't get this.
You can't get that. Okay, I will check the steps to see. So something that I just want to double check. You ran that exe file. Everything, there were some basic steps. Yes, at the end you saw that finish. Let's say selection, and you select the message, and then you select that finish, and this closes and nothing happens, and you don't have these installed software in your here. Okay, let me check this step again and see what could be that. Okay.
Okay.
I'll get back to you.
Could it be? What about maybe the system, the laptop? Just inquiring, my friend.
Maybe. Especially, you should have administrative admission. Okay, you should be admin of your laptop. Your account should be admin. This is necessary.
Okay, maybe I can check on that because I'm the admin. Let me just find out also from my laptop and see.
Okay.
And maybe the laptop specification 32 or 64, something like that. I don't know.
64.
Oh, that one is okay.
I will also check the steps to see if I can guess what could be the problem. Okay, and yeah, you also check that. Let's check both. So hopefully fix that.
Maybe others can also try so that we see if they are experiencing the same challenge.
Yeah. Mr. Alireza?
Yeah.
I sent a question similar to the conveyor belt you are teaching us yesterday.
Okay.
In your email, I was just requesting if you can go through it. We see.
Or you just send me. I
Tomorrow
will
or
check my
something.
email in the morning. Okay. This is PLC counter example. Okay, I will read and reply. Okay. Okay. Yeah. Okay. Sure. I will check and then reply you.
Thank you.
That's good. Very good. Any other question? Okay, very good. So see you next week on Tuesday.
Okay, thank you.
Thank you. Goodbye.
Bye-bye.